Okay, we're on one of our last chapters here. This is amines, and by now we've already covered a lot of amine chemistry because you've covered all the other functional groups. A nitrogen is very basic, usually because of its lone pair. It's not a strong base, usually still considered a weak base, but the lone pair can cause it to get protonated. So here's an amine functioning as a base. But we know that bases are also good, Lewis bases are also good nucleophiles. So this base could come in and attack a carbon electrophile like an alkyl halide. And we can get what we call alkylation at the nitrogen. Okay, when we do that, we usually end up with some kind of a positive charge, so sort of like an ammonium salt in this case, whereas here this is what we call the free base, which you usually only hear in terms of drugs like cocaine and stuff. But yeah, this is called the free base, and then this is called an ammonium or alkyl ammonium salt. Okay. And most of the drugs that we take, even like prescription legal drugs that we take, are in ammonium salts formations because those formulations are more stable. So often things like even lidocaine or drugs that like your dentist puts in gums to numb them, those are usually shelf stable in their ionic forms, so in their salt forms. And then as you deprotonate, you can get it back into its basic form, or pH changes, like in your tissues, releases it back into its free base form. So let's look at lysergic acid diethylamide, also known as LSD. And in LSD, which is known as a hallucinogen, a lot of musicians used to take this in the 60s. Causes you to see, I guess, vibrant colors. And I've never taken it, so I can't say, but that's sort of what people say, is that they see a lot of like interesting images. But anyway, in LSD, we've got several nitrogens. And we've got this nitrogen, this one, and this one. It's called nitrogen 1, 2, and 3. One of these nitrogens is significantly more basic than the others. So can you figure out, is it 1, 2, or 3? Which of these nitrogens looks like it's more basic to you? And why do you think that is? So when we look at how a nitrogen acts as a base, it really depends on the availability of the lone pair, right? So if the lone pair is not as available, then it's not going to be as basic. And by availability, I could sort of mention that in terms of resonance. So like in this first nitrogen here, we have an amide. And in amides, we know that we have resonance stabilization. So that means this nitrogen's not so basic because the electrons are actually delocalized into the carbonyl system. So to me, that doesn't seem very basic to me. Okay, so amides are much less basic than amines are in general. This amine here has a lone pair, and it doesn't seem to have resonance stabilization anywhere. So it's sp3 hybridized, and that lone pair is available to bond. So that looks pretty basic to me. This one over here has a lone pair. Looks like it's sp3. But if you look closer, you notice that there actually is resonance delocalization. And it extends actually both ways, that way as well as this way into the ring. So it turns out it's quite basic. This whole system right here is actually conjugated. So, and you can see that this lone pair is going to be the least basic then because of this extensive conjugation here. So in order of basicity, I would say this is the most basic. This one's less basic because of resonance here, and this is the least basic because of resonance all around here. So let's just put a note here, most basic site. So you always want to think about resonance when you think about bases. And in addition to resonance, you also want to think about induction. So let's look at this tertiary amine here.
that's going to have more induction or donation of charge into the nitrogen and its lone pair, making it more basic. So tertiary amines are going to be more basic than, let's say, primary amines, for example, because you have less induction, less R groups with their electron clouds donating in. So you need to think about both resonance and induction to figure out the relative basicity, and that's often a common question on the ACS final. Now, with properties of amines in terms of their physical properties, like boiling point, melting point, things like that, they vary quite a bit based on whether an amine is primary, secondary, or tertiary. So you see our primary amine has a boiling point of 50, the highest, versus triethylamine, a tertiary amine, has a lower. Now, the highest one, 50 degrees here, that signifies stronger intermolecular forces at play compared to secondary, tertiary. So why do you think that might be? Well, one thing you might notice is that these are all about the same molecular mass, so they're all the same. They're all the same formula. You can see that the primary amine has 2 hydrogens, so there might be more hydrogen bonding capability there. And you also see a longer carbon chain, and that longer carbon chain gives us a greater surface area. So in comparing these 3 amines based on the same molar mass, so isomeric amines, you see stronger intermolecular forces, both due to more hydrogen bonding and a longer carbon chain. Now with nomenclature, we follow the same rules as before. We number the longest chain. Now, one thing that I've noticed students do a lot is they confuse amides and amines. Remember, amines have just an R group, and amide has a carbonyl group next door. So you need to make sure that you know the difference, because their physical properties and nomenclature, it's really different. For amines, notice that the nitrogens can be substituted just like in amides, so we use the same capital N nomenclature for that, N-methyl, N-ethyl, and the longest chain is hexane. So we always go with the longest chain, and the ending is going to be amine. The amine is going to have priority over the other groups, usually over alkyl halides, so over halogens. And amines are equivalent to alcohols, so they take priority over double bonds as well. So this molecule is called a hexanamine, so that's the parent.
Here, chlorines have lower priority than amines. But it turns out we can number them lower at 2. So 2,2-dichloro, N-ethyl based on E, then M for methyl, alphabetical order. This one shows chirality. So this is a 1, 2, 3. That's counterclockwise. So this is S. All right, so let's practice naming these amine. Give these a try, and then let's come back and go through them. All right, so for this one, I got 1, 2, 3, 4 is my longest chain, 3,3-dimethyl butan amine. And that's because amines are higher priority. I want that to be the lowest number, so that gets the 1. You can say 1 amine, or you can just leave off the 1. Here, this is a cyclopentyl amine. Oops, I put cyclohexyl. Should be cyclopentyl amine. And cyclopentyl is a sort of a common name. We want to say cyclopentanamine if we want to use the systematic name, pentanamine. Okay, but cyclopentylamine is okay also. NN-dimethyl I did it again. Pentanamine. You guys are going to blame me if you get that wrong, huh? Cyclopentanamine. Make sure you have the cyclo part. Here, this is NNN triethylamine, but we often drop the NNN just because it's sort of redundant. But if you have triethylamine, it means that you have 3 ethyl groups, so they must be coming off the nitrogen. So triethylamine is sufficient. And then this one, you have R and S here. So this is S because it's 1, 2, 3, and that's going counterclockwise. This one wins over this one and this one because that's 2 carbon groups. So 1, then this one eventually has the nitrogen. This one has just carbon. So 1, 2, 3, that's clockwise, so that's R. And that's both of these are with priority 4 in the back. All right, so I'm going to name this as an amine. So this is a cyclohexane amine, right? But it's 3 isopropyl. And since I have 2 chiral centers, I'm going to specify 1s, 3r, 3 isopropyl cyclohexane 1 amine, or you could take out the 1, cyclohexane amine. And then this last one is going to be similar. Now here I can name it as a 3 amino cyclohexanol, or I could name it as a 3 hydroxy cyclohexanamine. And since we're in the amine chapter, I'll just pay homage to the amine. We'll say 1R, 3S, 3 hydroxy cyclohexanamine. And R is because 1, 2, 3, because this is an N versus a C versus a C. And this C wins because eventually there's an O, whereas this has a C and then a C and then a C. Okay, so that's R. Wait, 1, 2, 3. Oh, sorry, that's going this way. So that's going to be S. And this one is going to be 1, 2, 3, because this one eventually has the nitrogen closer. 1, 2, 3. But this one is 4 is in the front. The hydrogen's in the front. So I have to reverse that answer. So this one's going to be S. And this one looks like it's 1, 2, 3. That one's going counterclockwise. That one should be S. All right, so 1S, 3S.